Okay, great.
Okay, great. So welcome everyone to this week's colloquium. So this week we're very happy to have Netta Engelhardt from MIT. So Netta is a theoretical physicist who's really been at the forefront of a lot of very interesting recent progress in the last few years in the area of what you might call modern general relativity or quantum gravity, which is the same intellectual strain that Stephen Hawking worked in and that Roger Penrose, who just won the Nobel Prize, works in. So Netta, she got her undergrad at Brandeis, her PhD at Santa Barbara, and then she did a postdoc at Princeton, and then last year was hired as an assistant professor at MIT, which is a very rare achievement in our field. Usually you need at least 2 or 3 postdocs before you're competitive for any kind of faculty position. So she's won various honors and awards. She's won NSF Grad Fellow, a Blavatnik Regional Award, and a very significant one came just a few weeks ago, the New Horizon Prize in Physics. So for those of you who don't know, the New Horizon Prize is part of these Blavatnik, what are they called, the breakthrough prizes for theoretical science, which have become perhaps the most prestigious prizes in theoretical physics, other than the Nobel Prize. And they're certainly the richest prizes at this point, worth far more money than the Nobel Prizes. So as part of these every year, they award a few for young upcoming people who have done significant contributions to their field. So Netta was one of this year's winners for this New Horizons Prize. So we're very happy to have her, and please take it away.
Thank you, Kurt, for the really lovely introduction. And thank you all for coming and for waiting while I resolved various technical difficulties on my end. I apologize about that. So I'm very excited to be able to tell you about the recent developments on the black hole information paradox. And in particular, we'll call this in the age of holographic entanglement entropy. And what I mean by that is the fact that these new developments could not have happened without various other advances on the front of holography and holographic entanglement entropy and information within holography. So I'll say a lot more about this, but let me get started. I wanted to have a little bit of motivation first. So let me begin with some things that we know. We know that general relativity is not a complete theory of gravitational phenomena. Deep down inside black holes in the pre-inflationary universe, we know that general relativity breaks down. Now, we expect that this effective description of a decoupled theory limit of general relativity and quantum field theory, so basically what we approximate most of our universe today by, that is no longer valid in regimes like that. And we need something that can simultaneously describe very small things as well as very massive things, basically a quantum theory of gravity. Now, potential snag, we actually don't have something like that. We don't have a self-consistent, direct, non-perturbative formulation of quantum gravity. But I want to emphasize that without a description of the pre-inflationary universe and the deep interior of black holes, our description of the universe is currently incomplete. These things exist. So that leads us to the things that we don't know. In the words of Franz Cordova, the former director of the NSF, black holes are the most mysterious objects in the universe. And among the things that we really don't understand, the black hole interior. This is a beautiful picture by the LIGO collaboration of the in-spiral of 2 black holes, but that still is really only telling us about what happens outside. And sooner or later, we're going to have to confront the fact that these things probably have an interior, and we have to be able to describe it, to fully and completely describe our universe. Now, this is where the black hole information paradox comes in. It appears that we might need input from quantum gravity to understand physics in a regime that we didn't think we needed it. In other words, already at the event horizon. So at the event horizon for large enough black holes, we expect that semiclassical gravity is valid, and that information paradox appears to be telling us, at least a naive interpretation of it, is saying that actually we need quantum gravity already in a regime where we did not expect it to be necessary. which is very confusing. It wouldn't have been confusing if we had said, oh, we need quantum gravity in order to understand a deep black hole interior. That's fine. We expect that. We don't expect it to be necessary in a regime where we would expect semi-classical physics, in other words, some weakly coupled limit of general relativity and quantum field theory to hold. So this leads me to the information paradox. What and why? So what is it? The black hole information paradox is an apparent contradiction between the predictions of semi-classical gravity at the event horizon, where we expect it to be valid, and the unitarity of quantum mechanics. Again, this is a regime where we expect that everything we know about gravity and everything we know about quantum mechanics is still valid. There's no large curvatures that on small scales that happen near the event horizon of the large black holes, for example. So the caricature that you often see for the information paradox is that you have Alice and Bob. They're entangled. They're two observers. Alice ends up inside the black hole, and Bob doesn't. Now, that's fine, okay, but then the black hole evaporates, and Alice does not exist in the universe anymore. We seem to find that Bob has gone from a situation where he was entangled with Alice and both of them existed in the universe. We had this entangled state to a situation where Bob is essentially entangled with nothing. Bob is in a mixed state, which is the statement that information is lost. And so this is the caricature you often see of two entangled particles. One of them essentially disappears forever, and information is lost, which is in contradiction to the predictions of unitarity of quantum mechanics. Now, why do we study the information paradox was the what, and I'll say a lot more about the what in a few minutes, but let me say a few words about the why. I motivated in the previous slide why we are interested in studying quantum gravity, because there are phenomena in the universe that we need quantum gravity in order to describe. Pre-inflationary universe, deep interior of black holes. Now, we want to understand quantum gravity, and ultimately one of the reasons, I would say the primary reason, that we care about the information paradox is because it has the potential to teach us a lot about quantum gravity. So if we can get insight into the information paradox without having a direct formulation of non-perturbative quantum gravity, then it should give us a lot of information about what it is that we're doing wrong in quantum gravity, in the sense, why is there a paradox? So nature should not have a paradox. Nature exists, things happen. If we have a paradox, it's because we expect that we're describing something wrong. And so understanding the black hole information paradox has the potential to teach us a lot about gravity in general, quantum gravity in general. So a little bit more about the information paradox. Like many other aspects of physics, the information paradox has a history of these very long periods that are very quiet and very short periods of very, very frantic activities. It looks a little bit like a bit of a flat line and then a bunch of delta functions and more of a flat line. And this is again true of many different fields in physics. I find that at least in my field, the information paradox has more silent periods of silence and more frantic periods of frantic activity. Now, what is different about the new developments as opposed to what we knew before? Where is the big advance? Before 2019, before these new developments from last year, the general perspective, and not accepted by everyone, but this was sort of conventional wisdom, is that unitarity in black hole evaporation, so information conservation, would require some non-perturbative quantum gravity calculations. Semiclassical gravity just appears to be losing information. Now, you might say, well, maybe information is just lost. But if you wanted to preserve unitarity, if you believe that quantum gravity should be unitary, that the universe is actually unitary, then the general perspective was that unitarity requires some non-perturbative quantum gravity calculations, that we won't see it in semi-classical gravity. And what was so exciting last year is that we were able to do a purely semi-classical analysis that is in some sense a hallmark of information conservation. And most of us, certainly I, did not think that this was possible. Most of us thought that you would need non-perturbative quantum gravity to see something like information conservation. And what's been especially exciting is that this has also borne fruit as far as beginning to shed light on other aspects of gravity, of quantum gravity. Just like we had hoped that if we understand the information paradox better, we will learn more about quantum gravity. So here's a table of contents of my talk, which is apparently not showing. But roughly speaking, what I'm going to talk about, first, I'm going to talk about the information paradox then, in other words, before 2019. And afterwards, I'm going to talk about the information paradox essentially, well, up to in the years leading up to it, to 2019. I'm going to then take a little bit of time to talk about the holographic entanglement entropy proposal, because the main difference between the developments pre-2019 and the developments post-2019 is the use of the so-called holographic entanglement entropy. And since that is this critical ingredient, that is what I am going to focus on for some time. And then I'll talk about the information paradox now. What do we know now? How much further we've come? And I'll even have a speculative and audacious section where I talk about the information paradox in the future. I'm not going to claim to be a fortune teller, but just speculate a little bit on where I think we're going. So I'll begin, as many good stories in physics do, with black hole thermodynamics. So let me begin with Wheeler's Gedanken experiment. It's a very famous experiment in which you take a hot cup of tea and throw it into a black hole. Now, black holes in classical general relativity don't have microstates. So you immediately conclude from that, if something has no microstates, then it has no entropy. So you take this hot cup of tea, you throw it into the black hole. And since this hot cup of tea had entropy and the black hole doesn't, you end up decreasing the entropy of the universe. Now, one of my favorite quotes about entropy in physics in general is by Sir Arthur Eddington. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. This is Sir Arthur Eddington. So Wheeler was very bothered by this, and the fact that general relativity, which we like very much, appears to not be consistent with the second law of thermodynamics. And so he asked his student, Jacob Bekenstein, to reconcile these two. I should say that when I think about this, I realize that I'm probably being way too easy on my own graduate students. Now, Jacob Bekenstein actually rose to the challenge, and he said, okay, black holes actually are thermal objects. They have a temperature and they have an entropy. And this thermodynamic entropy is due to quantum gravity microstates rather than classical gravity microstates, which it doesn't have any. And that in particular, this thermodynamic entropy is given by the area of the event horizon over 4G h bar. So this was a real breakthrough. And I should say that there's one of the motivating pieces of evidence for this is that the area increases monotonically as a function of time in classical gravity. So this is Hawking's famous area theorem. Now, furthermore, these black holes have a temperature when they're close to equilibrium, which is inversely proportional to the mass of the black hole. Now, I want to emphasize something here, which is that this statement of Bekenstein's that black holes have a temperature doesn't make sense as anything more than an analogy in classical gravity, because objects with a temperature have to emit radiation, and black holes in classical gravity are perfect absorbers. So in order to actually calculate the temperature of a black hole, which is one thing that Stephen Hawking is very famous for, you need to work in semiclassical gravity. You have to include quantum corrections because, again, black holes in classical gravity are perfect absorbers. So let's talk a little bit about these black hole thermodynamics. So if black holes are thermal, then they should radiate. Now, if the temperature of the black hole is hotter than its ambient surroundings, then as it radiates, it shrinks, it loses mass. But because temperature is inversely proportional to mass, then as the black hole evaporates, it gets hotter. So it keeps on evaporating until it's completely gone. And in Stephen Hawking's original paper, he dramatically called it black hole explosions, because this gets just hotter and hotter and hotter until it's gone completely. So why don't we see black holes exploding all over the night sky? Well, for a black hole to have the right temperature, it has to be really, really tiny. So some numbers to ground us. So Sagittarius A star, current estimates of its size would put its temperature at about 10 to the minus 14 Kelvin. So significantly colder than the cosmic microwave background. This thing is not going to just evaporate in front of us. Now, a solar mass black hole is a little more promising, has a temperature of 10 to the minus 8 Kelvin. And a lunar mass black hole would be about the temperature of the cosmic microwave background. And just for amusement, a coronavirus-sized black hole would have a temperature of about room temperature. And I'm sure there's some conspiracy theorists out there who would absolutely love to have this information. So this is the reason that we don't just see black holes evaporating all over the place. They have to be extremely tiny in order to actually have a temperature that they would be evaporating. All right, so let's talk a little bit about this process of black hole collapse, black hole evaporation, just to see what it looks like. So first, let's talk about what we mean when we say a black hole is collapsing, because we will need that intuition in order to talk about what we mean by the black hole is evaporating. So here, this is a diagram of a star. So this circle over here that you're seeing, this is meant to be an illustration of some spherical star, which starts out at time t equals 0 and is going to be collapsing in on itself. So this star is getting smaller in radius as we evolve forwards in time. And at some point, it shrinks inside of its Schwarzschild radius, which means that an event horizon forms. So everything here inside is behind the event horizon. And as it keeps on collapsing, eventually it forms a singularity inside of the event horizon. So this is the process of black hole collapse. Let's talk a little bit about the structure of this space-time, what it looks like. So if I'm an observer sitting here at this point holding a flashlight, then this is where the light from my flashlight is allowed to travel, basically everything inside this cone. In particular, that means that in order to travel elsewhere, like here or here, I would have to be traveling faster than light, since this is where light is going. Now, as I get closer to the black hole, you'll notice that these light cones start to tilt. They're sort of starting to tip over. And indeed, when I'm standing at the event horizon and holding my flashlight, there will be this light cone will be tilted so that everything that travels more slowly than light is doomed to enter the black hole. If I wanted to escape the black hole, I'd have to travel outside of the light cone, which is to say, travel faster than light. There is one ray of light here which is able to stay on the event horizon. Now, as I get closer and closer, deeper and deeper into the black hole, my light cones keep on tipping over and over. And of course, the singularity is the inevitable end for any observer who enters the black hole. So this is we call the causal structure of the black hole, or what happens to the observer as he or she travels in. Now let's talk about evaporating black holes, so we get more fun pictures here. So what happens? Well, we have some star, we had this singularity, and this object starts to shrink. And eventually, as it shrinks, it gets hotter and hotter, and eventually it evaporates in some quantum gravity process that we don't understand. Here I've drawn the trajectories of the two particles that we talked about before, Alice and Bob, that one of them ends up being able to escape, makes it out to the infinite future, and one of them goes into the singularity. Now the paradox is what appears to be information loss between this initial state of the universe, where we had access to both of these, and the final state of the universe up here, where we would only have access to this one that makes it out to this final time. So there are multiple ways of potentially diagnosing information loss or information conservation in a system like this, but one of the most useful ones is in terms of entropy. In particular, the entropy of this radiation that is what is making it out to infinity, what we call the Hawking radiation. So here again, we have this dramatically simplified model, which is not particularly accurate, but it still gives a qualitative idea of what's going on. So we take an entangled pair. We have Alice and Bob. And so here we have some bell pair written down, and this falls across the horizon. So we have Alice, one partner in this bell pair is behind the horizon, one is outside of the horizon. Now, if we were just talking about the right particle, if we were ignoring everything inside of the black hole, we could still write a description of the right particle, but not in terms of a vector in the Hilbert space, but rather in terms of a density matrix, because this thing is in a mixed state, so we can't represent it as just a pure state or vector in the Hilbert space. So the right particle is a density matrix. It's this 1/2 times the identity. This is the maximally mixed density matrix. And one way for us to measure the purity, in some sense, of the density matrix, whether it is a pure state, whether it's a mixed state, is using something called the von Neumann entropy, which is often used as a diagnostic of unitarity. So what is the von Neumann entropy? For a given density matrix rho, the von Neumann entropy is defined as minus trace rho log rho. Why is this a valuable quantity for us? Well, it has a number of very nice properties. First, it is invariant under unitary evolution. That's already a good thing, because if we want to get a diagnosis of whether we get unitarity or not, then this is certainly something that we want from such a diagnostic. It also vanishes for a pure state, and only for a pure state. And finally, it is bounded from above by the thermal entropy, which we also call the coarse-grained entropy. So these three facts actually make it very valuable to talk about the von Neumann entropy as a measure of whether we fail to have unitarity or not. Now, why do we call failure of unitarity here information loss? Just a little bit of intuition. We can quantify in a very rough way the information in a state in terms of the difference between the thermal entropy and the von Neumann entropy. So in a thermal entropy, you have maximal ignorance. And if if the actual entropy of your state is smaller than the entropy of the thermal state, then you don't have maximal ignorance, which means that you have some information. So this is the rough intuition behind one of the pieces of rough intuition behind why this von Neumann entropy, we can think of it as quantifying information. So again, the thermal state is at equilibrium, contains no information. So if a system starts out at some small von Neumann entropy and it evolves to a larger value of the von Neumann entropy, then it is getting progressively closer to a thermal state. And so the difference between is getting progressively closer to a thermal entropy, and the difference between the thermal entropy and the von Neumann entropy is getting smaller. And so we are losing information. Now, alternatively, another way that we can think of this is we think of the pure state as the entire system. So a mixed state can always be purified by the addition of another system. So if you think of a pure state as the entire system, then the von Neumann entropy can serve as a rough guide of how short we are of having the full system. And in fact, this is one of the ways in which we can talk about why it's so uncomfortable to have information loss. So in physics, we like to be able to make predictions. And in fact, we think that physics is a predictive science. Also, it's a postdictive science, which means if we have all the information in the current moment in time about the entire universe, then we should be able to use equations of motion to evolve it backwards in time. Now, if it happens to be the case that we started in a pure state, we ended up in a mixed state, and then we take that mixed state and we try to evolve it back, well, what we end up seeing is we actually can't, because we don't have access in some sense to the full system. So this failure of post-dictivity is very uncomfortable from the perspective of what we expect in physics in general. Now, I should say this evolution from a pure state to a mixed state happens all the time. So if you don't see the problem in what I just said, then maybe you're thinking of something like a tabletop experiment. You have a tabletop experiment, you have an open system, it interacts with its surroundings. It settles down to a thermal state, and it loses information along the way. But that, of course, is because open systems don't evolve unitarily. And that's fine, it interacts with their surroundings. But what do we mean by the surroundings with the entire universe? The entire universe is not an open system. And this is why we expect that if we have the state of the entire universe, we should be able to post-dict everything that happened to lead to that state. But a failure of unitarity, information loss, would contradict that. And that would mean that physics at its core is not post-dictive, which is, it goes against everything that we have seen and everything that we expect. Which is not to say that some people don't subscribe to information loss. I'm simply motivating why we might not like it. So let's talk a little bit about the simplistic model of the EPR pair. initially, if we take the state of the pair, then this is a pure state. The Bell pair, if you include both particles, is pure. So the initial entropy is 0. Now, after the black hole has finished evaporating, the left particle is just gone from the system. And that means that the entropy of the final state after the black hole is finished evaporating is just the entropy of the right particle. And the entropy of the right particle cannot be 0. It's actually log 2, precisely because the right particle is not in a pure state. It's in a mixed state. And we know that the von Neumann entropy of a mixed state is never 0. And so we find that the entropy went from 0 to log 2. So the entropy is increased. The system was not evolving unitarily, and the information was lost. So this is a caricature or a simplification, a simplistic toy model of information loss in the Hawking radiation. So now, more accurately, here's some more accurate perspective on this. Let's imagine that we take matter in a pure state. So we have the entire universe has some matter in a pure state. We take that matter and we collapse it. So that sphere that we had before that collapsed into a black hole, that sphere is in a pure state. And collapses, it forms a black hole. Now, let's think about the entropy of the radiation. This thing starts to radiate. So what do we mean by the entropy of the radiation? That's the entropy of the quantum fields that live outside of the black hole. Radiation implies this is not inside the black hole. So before the black hole starts evaporating, the entropy is 0. Everything is in a pure state. Now, as the black hole starts to evaporate, the entropy increases. So that's okay. Why is that happening? Well, now we have two interacting systems. We have the black hole interior and the black hole exterior. Stuff can fall in from the exterior into the interior. So this is two interacting systems. It's fine. We expect the entropy to go up. Now, the black hole now continues to evaporate, but the radiation entropy keeps on increasing. This is, as Hawking means, this refers to Hawking's calculation. And then the black hole just goes away, it disappears altogether, and the entire system is just the radiation, which saturates at the thermal value. So what we find, and really what Hawking found, is that the radiation doesn't have 0 entropy after the black hole finishes evaporating. That means that the end state is not pure. And so the universe evolved from a pure state here to a mixed state there. So if this black hole is the entire universe, then we have evolved from a pure state to a mixed state. This is the non-unitary evolution of the entire universe, and the entire system, which is closed, has lost information. So we have this very uncomfortable statement. A pure state in a closed system evolves to a mixed state. This seems to contradict everything we understand about quantum mechanics. Information is lost. So the question then becomes, is quantum gravity non-unitary? Or maybe there are some non-perturbative corrections that somehow fix this. There have been papers written on either possibility. I argued a couple of minutes ago why things being non-unitary is not very comfortable, but there are some people who subscribe to that. Now, you could ask, if quantum gravity were unitary, what would a unitary entropy curve look like? So this curve is called the Page curve. It's named after Page for proposing it. And this is a curve that you can see initially increases, but then eventually starts to decrease again. So what is happening here in this curve? Well, initially the entropy increases. Again, this is for the same argument that we made before. During this time, we have these two interacting systems. The entropy of these two, the entropy can increase, the entropy of the radiation. But eventually, when more than half the black hole has evaporated, the radiation should now, if the system is evolving unitarily, the radiation should now contain information about more than half the system. And that means that its entropy has to start decreasing because it is essentially purifying itself. So if the black hole evaporating somehow is unitary, then the entropy then the radiation has to end up knowing everything about the system. In other words, it has to end up in a pure state, which means it has to end up over here at 0. And so this time over here, which is a sort of idealized sharp thing, but no, really it would be slightly smoothed out. This is what we call the page time. After more than half the black hole has evaporated, the entropy starts to, the radiation starts to purify itself. So this would be what would happen if we had a unitary evolution of the evaporating black hole. So which of these is the correct curve in quantum gravity? And how do we calculate it? If we could calculate it, then we could get some more insight into the actual processes of quantum gravity that, if it's unitary, allow the information to get out. So again, table of contents is not showing, but this leads me to the next part, which is a discussion of holographic entanglement entropy. Because again, that is the tool that we used to really do the calculations of a unitary page curve using nothing but semiclassical gravity. So let me talk briefly about a preview of these new developments. So from the perspective of semiclassical gravity, it's really hard to see where Hawking's analysis went wrong. You look at it, he did things very thoroughly. It doesn't look like you can easily find a mistake. So it seems like if we are hoping for unitarity, then we need to find some ingredient from quantum gravity that would help us figure this out. What we found in the new developments is that a completely semiclassical calculation actually can give the unitary page curve. This unitary page curve that has information conservation actually can be seen from semiclassical gravity, but only if we use an interpretation of that calculation which is inherited from quantum gravity. And what do I mean by an interpretation which is inherited from quantum gravity? I mean an interpretation of a particular geometric quantity which we obtain from holography. And this finally leads me to the new developments that were necessary for this, beginning with holography itself, also known as the ADS-CFT correspondence. So the ADS-CFT correspondence, which often we use as a sort of a soup can drawing for this, is a duality between quantum gravity essentially sitting in a box, so with anti-de Sitter boundary conditions, which we call the bulk, and a lower dimensional non-gravitational quantum field theory, or conformal field theory, that we call the boundary. So here, this is one-dimensional string or M theory with anti-de Sitter boundary conditions, and this here is the boundary, d-dimensional gauge theory. Now, normally we work in the limit, where quantum gravity in this box becomes semiclassical gravity. But we are also free to work in a different limit, where we have full-on quantum gravity in the bulk. And the power of this statement is that it still holds. And it's the conjecture statement, but the power of this conjecture is that we still expect that non-perturbative quantum gravity has a description in terms of this d-dimensional non-gravitational quantum field theory. So in this sense, holography can be seen as one way of thinking about quantum gravity. All right, so what is the statement which is so useful for us from holography? Well, one of the statements that will be very useful is that a black hole is just another quantum system, right? A black hole inside this soup can is really just some state of this totally ordinary non-gravitational quantum field theory. So if a black hole is just another quantum system, so there's a beautiful picture here where we have a black hole in curved spacetime, and this just corresponds to some ordinary non-gravitational quantum system in the dual theory. So we seem to have a resolution of the information paradox here, which is that the quantum field theory evolves unitarily. And if it evolves unitarily, then automatically that implies that the quantum gravity theory must evolve unitarily. So since black holes are just ordinary non-gravitational quantum systems, they must also evolve unitarily. So ADS-CFT tells us black hole evolution is unitary. But of course, this is very indirect. It's not very satisfactory. It doesn't help us answer any question about the way in which information escapes, the mechanism that enforces unitarity. We hope by studying the black hole information paradox that we'll actually learn something about quantum gravity. This kind of tells us, okay, well, you don't have to worry about unitarity, but it doesn't tell us why. So can we get more from ADS-CFT? Can it actually tell us how information gets out, or why it gets out, or what is some more of the gravitational, what is the gravitational language via which unitarity is implemented. And so what is the idea here? How do we use ADS-CFT to do this? Well, the basic idea is going to be that we'll compute the von Neumann entropy holographically, but let me go through that in more detail now. So we already know if we compute the entropy in the bulk, again, inside the ADS box, via the usual formula. So S von Neumann rho bulk equals minus trace rho bulk log rho bulk. Then we get the so-called Hawking curve, information loss, where the entropy increases and eventually saturates. So in this picture here, we have rho bulk before the black hole has formed. That's this over here. So this is the state on everything that's on this blue slice, including behind the shell. So we compute the entropy of this. Then later we compute the entropy again of quantum fields outside of the event horizon. So here outside of the event horizon means the entire slice. Here it means specifically restricting to part. And finally, we compute the entropy at a late time after the black hole has finished evaporating. So again, this now rho bulk is the state of all quantum fields in the system, just like it was over here. And we find that the entropy, the von Neumann entropy of rho bulk T after is larger than the von Neumann entropy of rho bulk T before. So this is if we just do the Hawking calculation, the usual computation of compute S von Neumann using minus trace rho bulk log rho bulk. Now, let's compare this to what happens in this so-called back of the soup can in the dual non-gravitational theory. Well, there we have rho boundary of T before, rho boundary of T during, and rho boundary of T after. And if we compute the entropy in the CFT, in the gauge theory, using the usual formula, then we just get the von Neumann entropy of this equals the von Neumann entropy of that equals the von Neumann entropy of that. Basically, if you could do the calculation on the back of the soup can, we get unitarity. If we could do the calculation in the bulk using Hawking's method, we do not get unitarity. So what we would like to do is to find a way of doing the calculation in the bulk so that it is consistent with what we know has to be true from the boundary. So the idea, compute the entropy of the boundary from the bulk perspective, use the semiclassical bulk, using the holographic dictionary that relates boundary entropies to gravitational bulk quantities. So again, we want to compute a unitary entropy that we know works if we just use the CFT. We want to compute it using gravity, using the quantum gravity picture. And the way we're going to do this is use the holographic dictionary that tells us how to calculate entropies in the CFT in terms of quantum gravity. And the remarkable thing, which is shocking and miraculous to me, is that a holographic calculation of the entropy in the semiclassical regime using no non-perturbative quantum gravity does yield exactly a unitary page curve. So how do we do that? Well, let me begin with how we would calculate the entropy, the von Neumann entropy of the CFT using the bulk. But if we forget for a moment about any sort of quantum corrections to the bulk. So if we in the bulk, if you're working in perturbative quantum gravity or semi-classical gravity, we usually do a perturbative expansion. We say, okay, there's the classical gravity bit, and then we have various small corrections due to quantum effects, due to quantum fields propagating in the space-time. So if we just forget for a moment about quantum effects, and we only work with classical gravity in the bulk, then we can compute the entanglement entropy, the von Neumann entropy of the CFT using this following formula here. What is this formula telling us? It says that the area of a privileged surface X over 4gh bar computes the von Neumann entropy of a boundary state rho. What is this privileged surface X? It's the minimal area surface, which is a local extremum of the area functional. What does that mean? It means that if you take the surface and you do small perturbations of the surface's location, then its area doesn't change as a function of those perturbations to first order. So this is the holographic formula. It's a celebrated Ryu Takeyanagi proposal, or the covariant version, which is due to Hubini, Rangamani, and Takeyanagi. Now for a stationary black hole, so a black hole that doesn't change with time, for example, Schwarzschild, the so-called extremal surface that enters into this formula, just to give you an idea, is it lies on the event horizon. And since this is a stationary black hole, this area doesn't change with time. So now we're not quite satisfied with computing the entropy using just this formula here, because of course, black holes, in order for them to evaporate, we have to include quantum effects. Remember I said earlier, in general relativity, black holes are perfect absorbers. This means that we actually will not see the black hole evaporating unless we include quantum effects. So we have to include quantum effects. This formula works only to what we call zeroth order in GH bar, if we don't include quantum corrections. What changes when we include quantum corrections? Well, at first, if we just say, okay, let's include quantum fields propagating on our space-time, but we're not going to worry about whether these quantum fields actually interact with the metric in any way. We're not going to worry about whether these quantum fields have any kind of change the geometry. So this is what we call working with quantum fields on a curved background, because there's still no interaction between our quantum fields and our gravitational system. But we already get some corrections to the formula. So now the von Neumann entropy of a boundary state will be the area of this extremal surface, again, the surface that extremizes the area under small perturbations of its location, over 4GH bar, plus the von Neumann entropy of quantum fields that are outside of the surface. So if this is a moment of time in our bulk spacetime, this is the surface X, and this is everything outside the surface, then this is the state of the quantum fields, the density matrix of the quantum fields outside of X. And we add this contribution to the von Neumann entropy of the boundary state. This quantity is called the generalized entropy, coined by Jacob Bekenstein. So the von Neumann entropy of the boundary at this stage of quantum fields propagating on our background, but not actually interacting with it, is computed by this generalized entropy of this extremal surface. But this is not quite enough. Remember, for a black hole to evaporate, the geometry actually has to change in response to these quantum fields. So we actually want to work to one more order at least in this perturbative expansion. We want to ask, how do the quantum fields actually affect our geometry? And in that regime, how do we compute the von Neumann entropy of a boundary state in terms of the gravitational theory? And the way we do this is the so-called quantum extremal surface prescription that Aaron Wall and I proposed in 2014. So what does it say? Well, it looks very similar to the last one. It's the area of some privileged surface X over 4GH bar, plus the von Neumann entropy of the state of quantum fields outside of X. Sorry, chi, this is chi. The only difference between this prescription and the other prescription is, well, it's rather an important one. It is that the surface chi is not an extremum of the area. It is not a surface that, if you modify its location slightly, will keep the area fixed. Rather, it is an extremum of this entire quantity. So that is, if you take the quantum extremal surface, that's what we call it, quantum extremal surface, and you slightly modify its location, you perturb its location slightly, then the generalized entropy, this entire quantity, will be stationary to first order in these perturbations. So the difference between the semi-classical prescription that includes essentially all orders in the quantum fields interacting with the geometry, and just including the zeroth order contribution, is the fact that you're extremizing this entire quantity rather than just the area. So this tells us, in principle, how we should compute the boundary entropies from the bulk perspective in a system where the black hole actually evaporates. So this appears to be exactly the thing we want if what we're after is an understanding of the way that a gravitational theory can actually compute information conservation. So, and this leads us, with our mysteriously missing table of contents, to the current developments of today. So what are we going to do? Well, we are going to take an evaporating ADS black hole, and we are going to compute the von Neumann entropy of its radiation, but we're going to use the holographic entanglement entropy prescription, the quantum extremal surface prescription. So let's do this. How do we do this? Well, we sort of immediately run into a snag, which is that ADS black holes actually don't evaporate. To be completely technical, large ADS black holes don't evaporate. And by conservation of misery, we don't understand small ADS black holes. So what are we going to do? Well, we're going to force a large ADS black hole to evaporate. And to do this, we essentially extract the Hawking radiation by hand. So the reason large ADS black holes don't evaporate is essentially that the radiation can kind of bounce off the boundary, but they don't evaporate. The radiation can kind of bounce off the boundary and come back and keep on feeding the black hole, so it just equilibrates with it. But if we just extract the radiation, then the black hole has no choice but to evaporate. And this is effectively what we did. To be a little more precise, so here is a two-dimensional rendering of the calculation. Here is our gravitational theory, the bulk, and here we have a cold bath. So this is some CFT in its ground state. And at some point, we are going to couple these two. And now the bulk is allowed to radiate into the bath. And what happens indeed is that we get this interaction between these two, allow the Hawking radiation to basically escape. And we can model an evaporating ADS black hole, which we can actually understand. The hope, of course, is that the evolution of the full system is going to be unitary. So what do? Well, okay, we're going to apply the quantum extremal surface formula. And given that we know that a boundary state evolves unitarily, we're going to hope that quantum extremal surfaces correctly compute the entropy and give us a unitary answer. I should say that at the time, this was not necessarily a well-substantiated hope, because quantum extremal surfaces are defined perturbatively, perturbative quantum gravity. And it's not clear why they would know about unitarity if unitarity can only be detected by non-perturbative effects. But nonetheless, we decided to try it. So initially at early times, we have this, we look at this bulk state rho all, and we go to compute the von Neumann entropy of the boundary. So at early times, the minimal generalized entropy, the minimal quantum extremal surface is actually the empty set. It is the one that has the smallest von Neumann entropy, and therefore the one that contributes to this prescription. And therefore we find that the von Neumann entropy of the boundary is given by the von Neumann entropy of bulk quantum fields on a complete time slice. So far, the quantum extremal surface prescription hasn't made a jot of difference. But that's okay, because if you recall, the Hawking curve and the Page curve initially agree. Now, as the black hole evaporates into the external system, the von Neumann entropy starts to grow, because now there's an external system, so our systems are interacting. It's not closed anymore. After the black hole has evaporated half its mass, something really exciting happens. A new quantum extremal surface, whose generalized entropy is smaller than the empty set, appears. Now, in the prescription for the holographic entanglement entropy, we always take the von Neumann entropy of the smallest quantum extremal surface, the one with the smallest generalized entropy. And so all of a sudden, right after the Page time, right around the time where we expect that a unitary curve would turn over, but a non-unitary curve would keep on increasing, we see this new phenomenon. Just behind the event horizon, there is a surface that extremizes the generalized entropy. So the von Neumann entropy of quantum fields outside of it, plus its area, has a local extremum at this surface. And what's more, the area over 4GH bar of this, plus the von Neumann entropy of that, is smaller than the von Neumann entropy of just the quantum fields across everything. So what happens? What happens is, because it's smaller, the entropy of the empty set, because the entropy of this new quantum extremal surface is smaller, in fact, it starts to decrease. So this turnover, this change from increasing to decreasing, we can track exactly to this appearance of a new quantum extremal surface that computes an entropy which is decreasing with time until eventually it should go to 0. And so we were able to compute this unitary page curve, information conservation, using only semi-classical physics. I want to emphasize this point. So we took this formula, and this formula requires nothing, no computations about in quantum gravity. Areas of surfaces we can calculate in semi-classical gravity. The von Neumann entropy of quantum fields propagating on our spacetime and slightly interacting, we can also compute in non-perturbative in perturbative quantum gravity. There is no non-perturbative quantum gravity in this formula. In fact, this is exactly the state that would have given us the Hawking answer, a non-unitary answer, if we hadn't corrected it with this quantity here. So this is the von Neumann entropy of the boundary as predicted by unitarity. This is the entropy of the radiation computed using semi-classical quantities and satisfying a unitary evolution. So this is a great step forward, computing the page curve using only semi-classical physics. It's a big step forward, but of course, let me remind you, the reason that we are interested in the black hole information paradox in the first place is to learn more about quantum gravity. So we have to ask ourselves now, if this is the correct way to compute entropies in quantum gravity, then what microscopic quantum gravity physics justifies that? How do we justify this formula, which was a conjecture based on various physical intuition, but how do we justify that from some fundamental gravitational physics? Now, this leads me to a slight detour on how do we compute von Neumann entropies in the first place? So in general, we can compute it using minus trace rho log rho, but even not including gravity, this can be difficult to do. So we often use a different calculation, which we call the replica trick. So what we essentially do is we introduce n copies of our state, and we rewrite this identity over here. And so this computation here turned out to be, in many ways, sometimes at least, much simpler than trying to directly compute this quantity here. Now, so this is just a calculation for the von Neumann entropy. Now, if we think, okay, this is one way to compute the entropy of the radiation, how do we justify that this is equal to our gravitational prescription in terms of quantum extremal surfaces? So how do we do a gravitational calculation here? Well, we can relate trace rho for some unnormalized density matrix rho to the partition function. So again, there's a trace rho to the end over here. We can relate this to the partition function. In ADS CFT, we can relate the partition function of the CFT to the so-called gravitational path integral. So here the partition function for some unnormalized state rho to the n, this can be computed by a standard path integral calculation but evaluated on n copies of the geometry on which the CFT lives. So in particular, if we're working with Euclidean time, then we can compute trace rho to the n using a partition function on n copies of the CFT. So the gravitational ingredient here is we say, well, we can compute the partition function in terms of the gravitational path integral. What is this gravitational path integral? Well, it's very similar to the ordinary path integral, except instead of summing over fields, we integrate over metrics. So we set boundary conditions, asymptotic boundary conditions, and we integrate over all metrics. And what we integrate is e to the minus I grav. I grav is here is the gravitational action. Oftentimes, we can compute this using a saddle point approximation. So something like this, where here we're including the leading saddles. So what does that mean in terms of the replica trick? Remember, the replica trick is a way of computing minus trace rho log rho. And again, we want to compute S von Neumann rho boundary from the bulk. We want to justify the quantum extremal surface prescription. Well, on the boundary side, this turns into a formula involving trace rho to the n. Well, trace rho to the n, we can relate to the partition function on n copies of the CFT spacetime. And that, the partition function on n copies of the CFT spacetime, we can relate to a gravitational path integral that is computed from spacetimes with n disconnected boundaries. In other words, we ask, what is the gravitational path integral that where this boundary of the spacetime here is n copies of the CFT boundary. So let me give an example. Suppose we wanted to compute the partition function for n equals 2. Again, n here refers to this trace row to the n, so we're computing the partition function for trace row squared. But we are going to do this not using the CFT partition function, but using the fact that the CFT partition function can be computed by the bulk gravitational path integral. So what does that mean for us? It means that we take 2 copies of the ADS boundary conditions at infinity. Working in Euclidean signature, this just means we have 2 disks. And we ask, what are the saddle points that correspond to these boundary conditions? That will compute for us the CFT partition function for n equals 2, for trace row squared. Now, for 2 boundaries, there are 2 saddle points. There is the usual disconnected saddle point, which is just going to look like 2 copies of our space-time, say 2 copies of the black hole. And then there is this unusual saddle point, which is a connected wormhole between these 2 boundaries. These are 2 competing saddles. Now, in a fascinating turn of events, what was found is that the quantum extremal surface prescription, and I'm applying it to the radiation, actually can be completely computed in the case where, in certain cases at least, from the gravitational path integral exactly in this way, by writing the CFT von Neumann entropy in terms of a replica trick, and then by representing trace row to the n using the CFT partition function, and finally by equating the CFT partition function via the ADS CFT dictionary to the bulk gravitational path integral. Now, why do I bring up these competing saddles? These 2 competing saddles correspond to the 2 different quantum extremal surfaces in the problem. Initially, this saddle dominates, and this saddle corresponds to the empty set. This saddle will give you the empty set calculation. So the quantum extremal surface being the empty set, where we just include the entropy of the bulk quantum fields. Then we find that there is a switchover in dominance, and this replica, this solution, this saddle, actually dominates after the page time, after more than half the black hole has evaporated. And it is this saddle which is exactly responsible for this new and mysterious quantum extremal surface that saved the day in terms of unitarity. The switchover from increase in the page curve to the decrease is the switchover between these 2 different competing saddles in the gravitational path integral. So why am I telling you all of this? Is this actually informative? I mean, I just gave you a different way of doing the quantum extremal surface prescription, but what do we learn from that? Again, at the end of the day, what we want to do is learn about quantum gravity from the black hole information paradox. So what has this actually taught us? Well, before we ask what it taught us, let's ask, should we include these topologies, these weird saddles? You might think, well, why not? They're giving you unitarity. Of course we should include them. Well, yes and no. So the fact that the solution is a connected Euclidean wormhole means that this solution results, this saddle results in non-trivial correlations between the n boundaries. Okay, remember we had trace row to the n corresponds to n boundaries. Well, now we have incurred non-trivial correlations between the n boundaries. But remember, these n boundaries correspond to n quantum field theories that are completely independent of one another. These are n copies of n. These are copies of n independent systems. Everything between them should factorize. So if we want to include these saddles, then it seems that we have to give up on factorization. Having these correlations between n independent copies of the same system just doesn't seem possible in a single quantum theory. So if we have these correlations, that means that the gravitational path integral on n copies of this boundary B is not the same as the gravitational path integral on a single copy raised to the power n. And so if we go with the conventional wisdom that in ADS-CFT, the gravitational path integral computes the partition function, we find that the partition function of n independent systems is not the same, n independent identical systems is not the same as n copies of that partition function. So this doesn't seem possible in a single quantum theory, and that's very troublesome. Some possibilities? Well, okay, we're working hard. We're working hard on this in the sense that we would really like to preserve these saddles. They give us unitarity. They exactly reproduce the page curve. That cannot be a coincidence. So how can we reconcile the fact that we're getting something very unexpected for the partition function with the fact that it's also giving us unitarity? We want to keep it, but do we actually want to keep it? So one possibility that has been discussed in the literature is that the gravitational path integral computes an ensemble average, so an average over theories. That would certainly allow us to have this funny factorization. So the gravitational path integral wouldn't actually be computing a partition function, but rather an average over partition functions. Another possibility is that there's some non-perturbative corrections that restore factorization. And having access only to perturbative corrections, we haven't actually been able to find those non-perturbative corrections. And this leads me to the black hole information paradox, a view to tomorrow. So we're pretty sure that these exotic topologies are legal. We want to include them. They compute unitary evolution. They compute the page curve beautifully. But it does raise the question of what exactly is the gravitational path integral calculating? Clearly, it can't be calculating the partition function exactly. Either there are some non-perturbative quantum gravity corrections that have to go into it, or potentially it's computing some kind of an ensemble average, or maybe some third possibility that I haven't mentioned or haven't thought of. Now, there is one example where we actually understand exactly what's happening, and that's two-dimensional dilettante gravity. In that case, it appears to be that the gravitational path integral is actually doing a disorder average. And that in particular, it is doing an average over theories. In that particular example, we understand it. But it's not clear what this means, how that's supposed to work in higher dimensions. And we don't think that in higher dimensions it's going to do an average over theories because, for example, we know that there are certain instances of ADS-CFT where we have exact theories in higher dimensions. So it's not clear what this is telling us in higher dimensions. But what I would argue is clear, is that in recasting this problem in terms of quantum extremal surfaces and in terms of the gravitational path integral, we have pinned down a key ingredient on the resolution of the information paradox. The gravitational path integral is a key player. It somehow knows that there is unitary evolution. The only question is, how does it know? And there, of course, there are two questions really, at least. How does it know? And what is the actual calculation that it is doing to arrive at this unitary answer? What is the gravitational path integral computing? Why does it know what it knows? So some comments on the current state of the information paradox. Let's begin with a spoiler. We haven't solved it yet. So some questions that I have that I think are important. What entropy is the gravitational path integral actually calculating? If I wanted to compute minus trace rho log rho from the gravitation, using the gravitational path integral or not. In other words, if I just took what the gravitational path integral is doing and ask what rho, what state do I need to plug into the von Neumann entropy formula to reproduce what the gravitational path integral is computing, then I would like to know what is that state, because that is the microscopics of unitary black hole evaporation. What does an observer outside the black hole actually measure? So far we've talked about entropy, we've talked about unitarity as evidenced by the page curve. But if we were just standing outside a black hole and we were able to make arbitrarily accurate measurements, and we had a really, really good quantum computer, would we, on feeding these measurements to our computer, find a pure state or a mixed state? This is really, at the end of the day, the resolution of the information paradox, answering this question. Is the path integral doing an averaging of some sort? What is it averaging over? What are the constituents of a quantum theory of gravity? Is the semiclassical limit of gravity just an approximate description of some ensemble? And finally, what did Hawking forget? You look at his calculation and we have not been able to figure out where he went wrong. So what did he forget to include that led him to a different answer from quantum extremal surfaces? And so with that, I will thank you for your attention, especially given that I started late.
Great, thank you, Netta. So we'll open it up to questions. So we'll let the students go first if you have questions. So you can either raise your hand and talk or type into the chat. So let's see, Yu-Hao, do you want to ask your question directly?
Sure. Thanks for the talk. And so my question is, if two particles are entangled and one of them falls into the black hole, with the process of one particle falling into the black hole, break up the entanglement?
Thank you for the question. No, it wouldn't, because the interior of the black hole should still exist. And so in particular, we ask about the state of the entire universe. So we ask about a moment of time of the entire universe. So as long as the other particle exists in the universe, then entanglement hasn't been broken. The problem with evaporation is that once the black hole has evaporated, it's sort of taken that particle away with it. And you can no longer have any moment in time in which you could evaluate, in which you could take both particles and find that you have a pure state. So just the act of falling across an event horizon doesn't do anything. The problem is when the particle is removed from the universe by a black hole evaporation.
So does it mean the black hole evaporation actually destroys the particles?
Well, it destroys. Well, it appears to destroy the information. Of course, what we actually think, at least what I actually think, is that the information does somehow manage to get out. That would be if Hawking evolution is unitary, which again, I've hopefully given enough evidence to convince you that it is, then the information does get out and does not get destroyed, even though a purely semiclassical intuition suggests that it should be destroyed.
So let me pursue a little bit. So does that mean, say, according to the classical, say, general relativity theory, the particles should be, whatever falling into the black hole should be destroyed during the black hole evaporation process. But according to the quantum theory, quantum idea, the particles somehow can get out afterwards?
More or less. I would say general relativity doesn't really permit black hole evaporation. So really what you really mean is semiclassical gravity. So a situation where you're allowing the black hole to evaporate, but you're not, but you're basically considering, you're imagining that most of the evaporation can be described by essentially general relativity with very small quantum corrections. So if you make that amendment to your statement, then yes, that is more or less what the answer is.
Thanks.
Hey, David, do you want to ask?
Yeah, hi, thank you, a very good talk. So I guess I have a sort of naive question, which you sort of, I think, mentioned at the end of your talk, and as you were presenting these calculations done in, I guess, relating ADS and CFT, I was just thinking, is sort of the naive, so my naive guess for what did Hawking miss is something like, did he forget to worry about the entropy in all of the standard model fields? Is that just obviously not true, or is that what you're thinking, or is that not even a sensible question?
So that we could ask that question, but the way that Hawking did the calculation, he didn't do it for a specific set of quantum fields. So he essentially showed that a pure state at future infinity as well as a smooth state on the event horizon and a pure state on past infinity are incompatible statements. So it wasn't done for a specific set of quantum fields, which is why we would expect that it would still be true for all of the fields of the standard model.
Okay, thank you.
Annette asks in the chat, how is entanglement related to information?
So entanglement is information, I would say. So when we say, so in this bell pair picture, for example, what we really have are two qubits that are entangled with one another. And so when we say information loss, it could say, you could imagine what we essentially mean is that we have, it's the breaking of entanglement. So you have two particles that were entangled and one of them is gone from the system. So we have lost information. So the relation is, I would say, I would identify the two.
Great. Any more questions from students? Okay, Harsh, did you have a question?
Sure. I guess this was a very nice talk and very nice work. I guess I had one which was a sort of technical question, and then one was sort of more philosophical. The technical thing.
I welcome both.
They make a comment, which is, and maybe we can talk about the philosophical thing instead. Was just that, as I expect, that replicas have been used in in statistical physics since the 1970s, and I could recognize many of those annoying issues.
Yes.
You're dealing with cropping up again. So maybe I'll ask the philosophical question, which is that, so you provide.
Sorry, can I just respond to your more technical comment, if that's okay?
Okay, sure, go ahead.
So let me actually ask, are you by any chance referring to the, also to the, I think you might be referring also to the replica trick that is used in the computation of the free energy in condensed matter systems?
Right, yeah.
Yeah, so let me just make a comment on that because it's kind of interesting. So what you can do, and what we've done with a couple of my collaborators, is ask, okay, if these correlated replicas actually are contributing to the von Neumann entropy, then is this robust? Are they also contributing to log z? And so we actually did the calculation for a certain two-dimensional dilaton theory of gravity, and we found that at low temperatures, the free energy is, if you compute the annealed free energy, it's very pathological. But if you add these replica wormholes, then it begins to ameliorate the problem. But actually, it doesn't fix it. It's non-monotonic in temperature. It doesn't fix the problem, but it makes it a little bit better. And we find that the analytic continuation in the log z calculation is not unique, and that it looks like there should be a way of analytically continuing it that would get rid of the non-monotonicity. So this analogy that you bring up, the similarities, it's stunning. I mean, the spin glass analogy is really there. Yeah.
Well, that's very exciting. And it may actually fold in with the philosophical question now. I was going to ask, so you provided this very convincing, very nice argument that the evolution is unitary. But there are these people you said earlier who don't believe that it needs to be unitary even.
Yeah.
So how do we settle this question? Are there experiments one can do in an analog system where one could study this question, or do we just have to wait till they actually start observing exploding black holes?
That is an excellent question. So there are people who are asking if we can use ADS CFT, if we can use the relation between ADS and CFT to imagine modeling the CFT in a lab, because you say, oh, what if we're working with some two-dimensional CFT or one-dimensional CFT, and this is some strongly coupled system, and yeah, normally we have to work at large n, but maybe n equals 4 is fine, maybe n equals 5 is fine, and you can ask if you can actually model this. And I think that the answer probably is probably yes, that you could construct such systems, but you would have to take on faith that whatever you observe on these systems is actually describing a quantum theory of gravity. Now, because you would say, oh, but this thing must be dual to a gravitational system. But what we could do is we could ask, what is something that you don't know how to calculate from the CFT? And let's calculate it in the gravitational theory, something that is too hard to calculate in a CFT, calculate from the gravitational theory. And we don't expect it to be universal for all systems. And then you could ask, is it accurately and correctly computing what we are seeing in the lab? in this system that is in the CFT in the lab? And I think if the answer is yes, then I would say that's very strong and encouraging evidence that the answers we get out of ADS-CFT are correct, and then that the calculation that the CFT is doing for the black hole entropy really are reflective of what is actually, of the radiation entropy, really are reflective of what is happening. Now, again, that relies on, essentially we have to test the ADS-CFT correspondence and then say that with enough tests, we're willing to believe it. So it's not a direct experiment testing what is happening with the Hawking radiation, but I think it's maybe for now the most experimentally plausible thing that we could do.
Okay, so I don't see any more questions. So I guess we'll stop the recording part, and we'll see everybody next week.